non-singular transformations. So from the title, it is a kind of transformation. They are called non-singular if the following condition is true. So non-singular is only a terminology, but it means if for this transformation, right, linear, it is a linear transformation that we want to talk about because we're talking about the transformations defined by a matrix. For example, a certain t on x. So we're talking about linear transformations. So, and what condition this linear transformation is called non-singular? Suppose there is another transformation. We can denote it by T star. T star and T, we know this is a composite transformation. If you do two things like one after another, that is like a composite transformation. So this is another transformation. If this T star times T and also T star are both identity mappings. So if this is true, then we say T is non-singular. In other words, T is non-singular if T has an inverse, because we notice this transformation is essentially defined by the inverse matrix of T, of the other transformation. So let's look at a mapping T. So suppose T maps from its domain to codomain. So this is just a concept drawing. So to show that this first circle is the domain of T, and the other one is codomain of T. So I put domain and codomain for the T. And then if you have an X, which is the element of the domain. So suppose I put an X vector here. So it's an X from the domain. So then you can find image, right? This image will be Tx. Yeah, based on the definition of T. So you can always apply this mapping to X to get image. And then the T star on T, that means after you apply this, you apply T star. So if we look at this one, then you apply T star. So T star following the application of T. So then what do we get? T star, after you apply T. So this is the mapping T star T, right? That's the composite mapping. And you get X. That is, apply T star will result in X. So here is T star. T star T, because we, after we get image of X, that's the T, right? So T star T will be equivalent to an identity matrix. You see, for whatever input you have, the X, you still get X. So that is identity matrix. And then let's look at T star. What does that mean? So let's draw it differently. This time we apply T star first. So going to erase this, and we need to apply T star first. So this time T star is in fact a mapping. Suppose a mapping from the other side. For example, let's call it a Y. So an element Y. Element Y. So then you apply T star. This is now application of T star. So T star, then for Y element, you will get image of Y. But after you apply T star, we want to apply T. Apply T. So then this T so acting on the T star. You see, this is the first one we apply T star, right? So this is a T star. And then, so then what do we get? We get Y. We get this Y back. So that means this T and T star, no matter in what order. So right now we're showing T star is an identity mapping. Yeah. So if that's the case for this transformation, if T has such a mapping T star such that T star times T times T star are both identity mappings, then we say T is non-singular. In other words, T is actually invertible, and this T star is actually inverse mapping of T. So either non-singular or singular for a linear transformation. It cannot be both. So we just, if we can tell it is non-singular or not, right? So we can, so this is an important topic. So how do we find this T star? So if T is defined by this A matrix, if A is the transformation matrix for this mapping T, then T star will be defined by the inverse matrix of A. So T star is simply defined by the inverse matrix. From definition, we can tell that. Because we can also easily verify. So apply first T star T, right? This is one. We want to check if this is an identity mapping. So you just apply T first. So for this composite mapping, we apply T, Tx, which is its transformation matrix A times X. And then next apply T star. T star, which is defined by inverse. So then apply inverse onto this one, we will get the result. So using associative property, so it's we can associate these two together, A star A. And since that is A inverse times A. So because inverse times A should be identity, so this is clearly an identity matrix times X is X. So that shows if T star is defined by the A inverse, then T star times T will be an identity mapping. Similarly, we can verify that T star is also identity because T star is defined by A inverse. Then T is A. So we can verify T star will be a transformation with the transformation matrix, this one, A inverse. So that's obviously an identity matrix. So therefore, this mapping is an identity mapping because an identity matrix is corresponding to this mapping, TT star. So therefore, TT star is an identity mapping if T star is chosen as A inverse. Okay, so we know now for transformation T, linear transformation T, which is defined by A, its inverse transformation exists, which is defined by A inverse. And we denote the inverse by this here. So sometimes you can just simply put T with a -1 on the upper right corner, so to denote T star. So they're the same meaning. If you want, you can just simply say this is a inverse transformation for T, right? So in that sense, this T star or T, they're representing the inverse transformation. So you can choose the appropriate notation for this non-singular mapping. So far, we just realized that non-singular mapping is actually an invertible mapping. Its inverse can be found easily and defined by the A inverse of the original transformation. So let's look at the example. So here is a T. It maps a vector in R2 to another vector in R2. So you see domain, codomain, the same. It is the same site. And defined by a square matrix, 2 by 2 square matrix. Decide whether T is non-singular. So to decide whether this transformation, this linear transformation is singular or non-singular, all we need is to know whether the inverse exists, right? If the inverse exists, then we can use the inverse to define a mapping. And then that mapping will be defined, right, by this inverse matrix. You can put Y will be defined. Yeah. So yeah, we do not have to use Y. You can always say, okay, this is defined by the inverse matrix, and then you can use still the same X vector, just X is in R2. So it's just a matter of notation. This is a inverse mapping. So, and we know a convenient formula for 2 by 2 matrix. That is, for this matrix, if we do 1 over determinant of the matrix, determinant of the matrix, remember it is calculated by multiplying these two numbers minus product of the other two numbers. And you can see the -9 minus -12, which means plus 12. So 3 is the determinant. So determinant is not 0 because, okay, 3, non-zero. So it's invertible. We know whenever the 2 by 2 matrix has a determinant which is non-zero, then it's invertible. Then the inverse can be represented by this matrix. If we swap these diagonal entries, see we put -9 here, 1 here, and then do the negative numbers of the non-diagonal entries. So it will become 4, opposite of -4, and opposite 3 will be -3. So then this is the matrix. And of course, every entry times 1/3, you will get this. Yeah, this is the inverse. So if the transformation has a matrix yeah, transformation matrix A has an inverse, then this transformation, there's an inverse transformation for this T. What is the inverse transformation? It is simply this one. That means the inverse transformation is simply defined by the inverse of the transformation matrix, which is this one we just found. Okay. So it's to decide an inverse transformation, then it's a matter of deciding whether the matrix has an inverse. So let's look at a simple one. Here's a T. Yeah, it is a mapping, linear mapping from R3 to R3. So defined by the square matrix. So you input a vector from R3, you get a new vector, right? You get an image of this vector. Now suppose, okay, T is defined specifically by this transformation matrix. Now decide whether T is non-singular. So that is based on our introduction of this topic, non-singular. That means decide if T has, just decide if T has an inverse transformation. So let's use this matrix A. Do we have an inverse for this A? We see that this is a matrix that's an elementary matrix, right? It is different from identity matrix only by this. It's a scaling operation. So yeah, so this one elementary matrix is invertible, and its inverse is this one. You can check. You can check. A times A inverse is identity. Yeah. Or A inverse times A. They're both identities. So then we know this A is invertible, and the T has an inverse transformation, T star, which is defined by this A inverse, right? For any X, this is the T star defined by A inverse. So so there is the T star such that T star times T is identity. T times T star is also an identity mapping. So therefore, it is non-singular. So this A is non-singular. So let's look at another example. Here's another example from R3 to R3. The linear transformation is defined by a different matrix. Decide if this linear transformation T is non-singular or not. So we look at this transformation. It is also an elementary matrix, as we know from the previous topics. So you notice how different this matrix is from the identity of 3 by 3. Identity matrix, you see only the swapping of the first two rows of these two. Yeah, first row, second row, if you swap them, you will get an identity matrix, right? They differ from identity matrix by one elementary row operation. So yeah, this is an elementary matrix. And then we know the inverse is itself. Therefore, this linear transformation has an inverse. It is non-singular. This inverse matrix is exactly same as A. So if we define a linear mapping by this matrix A inverse, then this linear mapping times T will be identity, or T times this mapping is also identity. So we know that T is non-singular by definition. Here's another one. This one, immediately we see this is also an elementary matrix. It's just from the identity matrix, right? We see by replacement of the third rule. Yeah, it's a elementary matrix. We know actually each elementary matrix has an inverse. Therefore, it's also non-singular. If you want to tell exactly the inverse for this one, it is another elementary matrix. You see, inverse of this matrix, right? It's very similar, but with a negative sign here, -3, and you can easily find the inverse if we use the program I introduced in the previous lecture. So just to put the A matrix, suppose I want to find the inverse of this matrix, I put A and identity matrix side by side. And then if I reduce the A to identity, then the identity will become inverse of A. So here this is, we arrange first A and identity side by side. So the A, how can I make it identity? All we need is to do a replacement of the third rule. So keep the first rule as is, second rule as is, third rule, do a replacement. So the first rule times -3 will be added to the third rule to make it 0. So we get a 0. We still have 0. Add here, this 1. No, -3. This becomes -3 because the first rule, in order to make it 0, so first rule times -3 is being added to the third rule. So this becomes -3. And then it's 0 here. This becomes -3 because this one times -3 added here. So then this everything else will not change because multiple of 0 add here to still 0, and add to 1 is still here. So then we discovered this as inverse. That's the matrix inverse found. So just one step we can already find the inverse of the given elementary matrix, this one. So if the inverse exists, then the inverse mapping is just defined by this inverse matrix. Therefore, this mapping T is non-singular. So far, characteristics of non-singular transformations, we can identify a few now. That means T is non-singular if and only if A has an inverse, right? That's one characteristic that we have used, because in that case, A inverse will define a mapping. Suppose A is a square matrix, then we can easily say A inverse also from Rn to Rn. So if in that case, the T star simply defined by this A inverse, then you can verify T times T star is identity. T star times T is also an identity mapping. In that case, we can always find T star such that these two are both identity mappings and T is non-singular. So that's one characteristic. And additional ones, yeah, so we already noticed T, if this linear transformation is non-singular, it means the matrix A is invertible. It has an inverse. That means we can find some matrix, which is the inverse of A, right? So the some matrix, we can call it C. C times A is identity. Yeah. We can also find, for example, a matrix D, which is also inverse of A, such that A times this inverse is identity. But as I remarked earlier, we know that if there is a matrix, you can, if this condition is true, then that automatically implies the other condition. So these two are equivalent. For example, one implies the other. You don't have to verify both. So all we need is just to show one, because once this is true, then the other one is also true when we discuss the inverse matrices. The matrix A, if it has an inverse, you can reduce matrix A to an identity matrix. That is actually, we used the algorithm to find the inverse of A, right? Through reduction of A to identity, then we can find the inverse. That it was the algorithm. So all these are equivalent statements. And then from the equivalent statements, that means this, and yeah, they're all implying each other. So that means if a matrix A is invertible, the A, each column has a pivot element. Yeah, because the A can be row reduced to an identity matrix. So each column has a pivot element. And also we can know that this matrix equation has exactly one solution for each B. As long as B is given, then you have exactly one equation because A is invertible. So X can be found uniquely, just one unique solution. So whenever A is non-singular, you have a unique solution for the linear system. For each B given, you have a unique solution. And that means it's, yeah. We also have the conclusion that this has only one solution when B is especially a vector 0. So if B is a special case, if it's 0, then you also have just exactly one solution. What is that solution? And then X will be A inverse times the 0 vector, which is just 0. You have only a trivial solution. So that means the mapping defined by A will be 1-to-1, because we know if a homogeneous system has only a trivial solution, it is a 1-to-1 mapping. On the other hand, if it's non-singular, it is also onto. Because for each B in Rn, you can find an X whose image is B. Therefore, each B is image of something, some X. So that means any B from this space is an image of the transformation. So it is an onto mapping. Yeah, that also means any B from this Rn can be generated by the columns of A. So all these statements are equivalent. If we have this T as a non-singular linear transformation. So it's a just meaning the A matrix corresponding a non-singular linear transformation if and only if all the others are also true. So that means this linear transformation is not only one-to-one, also onto, also a unique solution for the homogeneous system or general case, non-homogeneous system. So that is a list of equivalent statements. So let's decide if this linear transformation is non-singular or not. So this linear transformation is defined by a 3x3 matrix A. To know if it's non-singular, let's see if there's an inverse. So how do you decide if there's an inverse? You just, you can try to look for it. If you can find one, or if you rule reduce to identity matrix, then you know it is invertible. So we start with A, we do row reductions, and then eventually if you do not get an identity matrix, that means A is not possibly be reduced to an identity matrix. There's no inverse for A. So I just mentioned the above equivalent statements, right? A is a non-singular linear transformation if and only if A has an inverse, if and only if A can be row reduced to an identity. But now this A cannot be reduced to an identity matrix. Therefore, it is not singular, it's non-singular. So no, it is singular because it's not non-singular, right? It's not non-singular, so it's singular. All right, so it's a singular matrix. That means this T does not have an inverse mapping. Okay, so we already talked about the linear transformation defined by square matrices. And so if A is such a matrix with columns span the whole entire space, then this A should have an inverse. So as long as you have a matrix A whose columns will span the Rn, that means A is onto. And if A is onto, A defines an onto mapping, then it has an inverse. Yeah, so I mention again the statements that I mentioned earlier. So if it's onto, it's also equivalent to non-singular. So they're all equivalent. So you just see whether if the columns of A span the entire space Rn, then you can tell it's non-singular. So all this can be used to tell from one to tell the other property. Okay, that's all for now.